For our next talk, I'd like to introduce Pavel Odintsov, who will be presenting network telemetry on modern routers. Pavel is co-founder and CTO at FastNetMon and is coming to us today from London. This is Pavel's first time presenting at NANOG, and it's a pleasure to have him speaking with us today. Welcome, Pavel.
Thank you for coming, everyone. I'm Pavel. I'm a Chief Technical Officer for a company called FastNetMon. And what we do at FastNetMon, we develop on-premise DDoS detection solution. And one of the options and distinguishing features of our product that we use open source code. And I have been doing it more than 10 years, and I would love to share our experience collected over from perspective of software development, from point of when we developed our product, and from different perspective of operational experience in different telemetry protocols. So I'm very open for any kind of feedback. I would love to share latest changes and latest improvements in telemetry protocols, and there are many ways how you can actually contact me. In this presentation, I will talk a lot about different protocols in different implementation by vendors. But different things, they may be used for very different purposes. In this presentation, I will be focused on using on telemetry protocols for purpose of DDoS detection. And purpose of DDoS detection is quite different, for example, from different applications like audit purposes or SIEM purposes. What is different for DDoS detection? In DDoS detection, we care a lot about latency because we want to observe DDoS attack as fast as we can. And second case is that we deal with incredible amount of data, because attacks, they may consist tens of millions of packets, hundreds of millions of packets, and it puts more challenges for us for implementation side. By saying modern routers, it may sound unusual. Now, what I'm trying to say, in this case, I mean routers of class Juniper MX, Cisco SR9K, latest models from Nokia, Extreme, Arista. That basically, by me saying modern routers, it's equipment you can buy right now from vendor, which is still supported, can carry and run a latest firmware, and then by saying it, you can use the latest development, the latest protocols available with this equipment. There are a lot of protocols available in modern routers. On this slide, you can see every single of them. And if you just start your journey in network telemetry, it may be very misleading and very challenging. What does those numbers mean? What is the best for my case? What should I do? Why? And I hope I will explain and provide insights in what is the best protocol for your specific case. I would love to start from Netflow 5. Netflow 5 is the oldest protocol, and I believe it's one of the oldest and still widely adopted protocols you may find on your equipment. This protocol uses fixed packet format. By saying fixed, it means that every single field a router can send to your monitoring device. It's fixed. It cannot be changed ever. It includes some basic information more for service purposes, like time when a specific flow was observed. But more important, what we care about is information about traffic. It's source port, destination port, packet length, source ASN, destination ASN number. That's actually information we care about to understand what happened on our network. But again, this protocol is fixed. Working with fixed protocols is very simple because you can parse it from Python, C, Ruby, different languages, and you just need to iterate over field by retrieving them. But what is the issue? Again, it's very old protocol. And back in time, when this protocol was designed, we had no IPFIX. So basically, you have no options to encode IPFIX, and you have no options to have visibility into IPFIX protocol if you use Netflow 5. And a very similar story with ASN numbers. It's very important for us to understand what is a ASN number we got traffic from, or what ASN number we send traffic to. And again, when this protocol was designed, it was just 2-byte ASN numbers. And if you deal and interact, and you do, with 4-byte ASN numbers, you will not have this information. And the purpose of staying and explaining why this protocol is still used, because there are still software issues, there are still routers which you can operate. And understanding how this protocol evolved is very important for understanding what is the benefits in new protocols. There are lots of information available in Netflow 5, and it still has benefits. Because, for example, if you are very limited on engineering resources and you have very old equipment, you still may use it. But if you have no old equipment, please don't use it. So there are multiple issues with this protocol, and let's move forward. This is curious stuff. It's not history. It's one of the more widely adopted protocols you may find in industry. It's used by everyone. You can find it in modern routers. You can find it in modern collectors. And at FastNetMoon, we use it a lot. And Netflow 9 is a really great protocol because basically we talk about network telemetry. But this protocol can encode literally everything. It can encode source IP. It can encode packet length. It can encode ASN number. But at the same time, it can encode any information you can imagine. And if you're a vendor, you may encode your pet name and send to collector. Why not? Because it's still field. And this protocol provides tremendous flexibility. And we have basically thousands of fields routers can export to us. It may be VRF ID, it may be subscriber ID in case of mobile networks, it may be some specific field, for example, for like TTL or TCP ACK number, everything. And how to accomplish it? In case of Netflow 5, which was fixed, you know what is the location of specific data in packet. Like, for example, you know that by shift of 10 bytes from the beginning of packet, you can find packet length and read it easy. In case of Netflow 9, it's way more complicated because every single device by different vendor, even for example, the same devices from different slightly different configuration, they may send different fields. For example, your router may have information about ASN numbers, but at the same time, your switch has no idea about ASN numbers. And in this case, we need to share this information from router to collector. And it's accomplished by sending packets called data templates. And data templates is basically a guidebook, how to decode data which will be sent by router to collector. And routers, they announce this data templates from time to time. It's like guidance for every single collector in network, how you can decode it. It's saying, by shift of 10 bytes, you can find source ASN. By shift of 15 bytes, you may find VRF ID. Easy. And it sounds easy. But for Netflow or collector implementation side, if you're a developer or system engineer working with it, it's basically a nightmare. Because what I just explained is just the beginning of the story. Because to retrieve information, for example, source IP in Flow, you just need to decode data template, which is announced by router from time to time, and then apply this guide to parse data about traffic. But if you use sampling, should I use sampling? You have to use sampling. Because back in time when we operated networks like 10 megabits, 100 megabits, 1 gigabit, it was still possible to export information about every single net flow observed by network. But in terms of networks starting from 10G, 100G, 400G, 800G, it's still impossible. So every real deployment of Netflow protocol have to use sampling. And sampling encoding is deadly complicated because just to retrieve just field of sampling rate. What is sampling rate? Just single value which says, when I observe one flow from router, it means actually not one flow, but 10,000. But to retrieve this information from Netflow 9, you need to implement a very complicated logic because there is a different type of packages used by routers to announce information about sampling rate. And at the same time, because of tremendous flexibility of Netflow 9 protocol, these data can be very flexible. So, and again, to be able to decode all information sent by your routers, you need to decode 4 types of packets. Templates for data itself, templates for options, which carry information for sampling rate, and data packets for which actually carry sampling rate. Sounds complicated, but fortunately it's not your problem, because in many cases it will be sorted by Netflow collector developers. And there are a lot of benefits in protocol Netflow 9. It works by literally any available router on market. It supports IPFIX. It can carry lots of additional information useful for your case. It may be information useful for DDoS detection. It may be information useful for security purposes. There are lots of them. But what are issues with this protocol? As I explained, one of the problems with this protocol is tremendous flexibility. It provides a lot of options what you can actually accomplish by using this protocol. But there is a downside. We have no documentation how actually Netflow 9 works. Because back in time, this protocol was developed by Cisco, but now it's supported by every single vendor we have on market. But we never ever had proper standard which actually explains how it should be done. But if we have no, but even, for example, for many things we have standard. And even by having standard, we have different violations and different misinterpretations of protocols. And then different vendors implement a different way. But in case of Netflow 9, we never had protocol, which leads to many issues. As I explained, you can see extraction of sampling rate is a tremendously complicated protocol. And that's the reason why in some collectors, especially for modern routers, for example, new models from Nokia, you may face issues that sampling rate cannot be decoded. And what exactly happens in case of Netflow 9? Because it never had any documentation how it should be encoded. And that's the reason why different vendors, even different routers from same vendor, decode it slightly different way. But again, it's an issue for your developers or for a company in charge of developing your network monitoring software. But again, in many cases, you may want to implement it on your own, and then you face this kind of issues. Well, let's move forward. IPFIX. IPFIX is a successor of Netflow 9. I believe early versions of IPFIX, they were called Netflow 10, which just highlights like similarities and inheritance between protocols. Because basically IPFIX is a well-documented version of Netflow 9, which actually has standard. Does that mean that everyone using Netflow 9 have to migrate to IPFIX? Not actually. And there are many examples on market of devices supporting only Netflow 9 and not supporting IPFIX. But in some rare cases, you may find some devices supporting IPFIX but not supporting Netflow 9. What is the difference? Because it's exactly the same design as Netflow 9. It's exactly the same unlimited flexibility of options to extend protocol. But at the same time, this flexibility, it comes with great deal of documentation, because we have RFC about data formats, templates, always of all types of data which can be encoded. And if you struggle to understand what's going on, what this field means, what is, for example, like next hop BGP, what is the difference between that hop BGP and next hop, just simple next hop. You may open RFC, you may Google it, you may find it, and problem solved, which is great. So basically, I would say IPFIX is work on mistakes made in Netflow 9, and which is great, which clearly highlights that this protocol is a new generation, and it solves many problems. But there is a problem. Everything, as I explained it, encoding of sampling rate in Netflow 9 is very complicated because we never ever had standard. And that was the reason why different vendors use different approaches to encode the sampling rate. And of course, IPFIX has to include this issue as one of the key requirements for new standard. But unfortunately, it's not what happened. In IPFIX, there are no single way how you can actually encode sampling rate. In standard, it doesn't limit you about with how you can implement it. It actually provides at least 3 different, completely from ways how you can implement sampling rate. And what we have, unfortunately, different vendors decided to use different ways how they encode it, because again, standard is too relaxed. It says, you may use this approach, you may use this approach, or you may invent your own. That's what exactly vendors did. So sampling rate didn't improve. It's still a nightmare to parse. And for example, if you may find some Netflow collector software which actually can retrieve information about sampling rate from Netflow 9, but it may struggle to retrieve this information from IPFIX. IPFIX has all modern requirements to deploy in your network. It supports IPv6, it supports 32-bit number ISNs, it can carry a lot of information, and basically everything you need. Issues. And issues are more about implementation. Because again, protocol provides unlimited options to export any information from packet observed by router or switch to your monitoring software. But it's up to vendor to decide which one is important. Because, for example, for us, for DDoS mitigation purposes, it's crucial to have information about TTL field. And unfortunately, almost none of the vendors, they think that TTL field is somehow important. And we cannot change it because in many implementation list of fields exported by routers is still limited. So protocol provides unlimited flexibility. You can export anything, but again, you are limited and constrained by vendor. And it poses serious issues for us because we cannot have access to information about traffic, which is very important for us to understand, is it attack or not. There is one next protocol. It's called sFlow. I would like to focus a little bit about naming. As we had conversation about Netflow, of course, protocols of family Netflow, Netflow 5, Netflow 10, and IPFIX, they operate on flow basis, which means in your routers you have flow aggregation engine, which tracks all new packets, all new flows, and maintains flow tracking table inside of router. So it operates on flow basis. sFlow was created initially mostly for switches. And switches, they never ever operate on flow basis. And basically, this protocol has nothing to do about flows. If anybody will ask me about what is the best name for a protocol called sFlow, it had to be named as packet. So, from design perspective, this protocol somehow similar to Netflow 5, but it's way more modern because again, list of fields we have is fixed. There is some basic meta information about source port, destination, source interface, destination interface, source ASN number, destination ASN number. But how they address that issue is a limited set of options explaining packet itself, properties of packet, like, for example, TTL field or packet length field. They use great trick. They use trick to, instead of parsing packet and sending it field by field, they just cut first 80 bytes of every single packet as it observed by switch or router, wrap it into UDP format, UDP payload, and then send to collector device. What it changes? It provides tremendous improvement for us, but at the same time, it provides tremendous challenge for us. How? Because instead of asking their vendor, can you add TTL field for my list of fields in IPFIX or Netflow? What we can do in case of sFlow, we just receive packet information, first X bytes, usually it's between 18 and 100 bytes of packet, and then we can find out what is the packet length. But problem is, it may be way more challenging for developers because you have to implement complete parser. So instead of just picking up one field, which may carry information about TTL, you have to parse, you have to find out, is it Ethernet header? And then you need to strip VLAN headers. And then you need to find out, is it just simple VLAN or it's double target VLAN? Do we have any MPLS input? And then finally, you may retrieve field which carries TTL field. So it's more complicated, but it provides more flexibility. On paper, sFlow protocol is just perfect. And the main issue with sFlow protocol, because what I explained, if it's implemented correctly, it will work just perfectly fine. For us, as the DOS detection company, it will solve all issues, all problems, and basically we have to stop looking for new protocol. But main issue is almost every single vendor we had experience with has issues, serious issues with sFlow implementation. And many of them make it effectively unusable. It may be some very weak CPUs which cannot export all information. It may be some configuration, unreasonably high sampling rate configuration, which again makes precision monitoring impossible. But it's a great protocol itself, it's a great idea, but problem is implementation in many of the cases. Port mirror. Port mirror feels like simplest protocol, a way to monitor traffic, because you can just list it up and look what's going on. Maybe it was that way when we had 10 megabits network, 100 megabits network, maybe even 1 gigabit network. But problem in modern networks that we have a lot of traffic. But again, if your equipment for some reason has no support for sFlow, for Netflow, and none of the modern monitoring methods you have available, so you still can use port mirror, even if your router has no support for port mirror itself, which is the case for many vendors. You can just use optical splitters and just deliver copy of information coming from your upstream to monitoring device. Sounds simple, but operational experience for port mirror for different purposes. In our case, it's the DOS detection. But again, for the DOS detection, we have to deliver every single byte of attack to monitoring machine. It may be tens of gigabits, it may be hundreds of megabits. In the worst cases, it may be up to a few hundreds gigabits of traffic. And this traffic has to be delivered. But first of all, you need to have spare ports on your router, plenty of them. And that's not something we have. Again, also you need to buy very expensive network cards for your monitoring machine. And if, of course, every single network we operate, if it's a real network, it has to be distributed. It may have multiple locations, multiple countries, and multiple metropolitan areas. And you have to deliver all traffic for port mirror to single location. It's basically, you need to double capacity of your network, which makes use of port mirror not very reasonable. And at the same time, in port mirror, we observe traffic as it is seen during transit. And we have no access to information, meta information from data plane. We have no idea what is source ASN number, what is VRF We have no idea what was, for example, source interface or output interface. This information is basically missing in case of port mirror. There is a small improvement. Unfortunately, it's not widely adopted, and the only vendor I know which actually supports it is Juniper in their Juniper MX router series. It sounds very simple. So instead of delivering every single packet, for example, for 100G, it's up to 144 millions of packets. It just picks up one packet from 1,000 packets. And this approach reduces the amount of data you have to deliver from router to your monitoring machine by 100 times, by 1,000 times. So you need to have less capacity to connect your monitoring machine. You need to have less CPU resources to parse it. So it makes it reasonable, even if you have no different options other than port mirror. Sampled port mirror is a very reasonable option for you as workaround. And this one is an endgame protocol. This protocol handles and addresses every single problem, every single complaint, every single concern, every single issue we had with protocol. Because we have multiple networks of scale exceeding more than like a few terabits of capacity. And many of those networks, they came this way, as I explained in this presentation. They started from Netflow 5. They faced issues with IPFIX. They moved to Netflow 9. They faced issues with Netflow 9, lack of some data. They moved to IPFIX. Some of them, they had to resort to move, in some cases, to sFlow, but they still had issues. And this protocol addresses every single problem we had. And every single, majority of our largest customers, they in process of migration to this protocol. But problem is, this protocol has no name. And what makes for me it's quite challenging because every single time on conference I had to use different ways what it does. That's why it's called weird way, payload via IPFIX. Even more interesting, it has to be full name of it. It's aggregation-less payload via IPFIX telemetry protocol. Because it's not new protocol exactly, it's a way how vendors decided to use IPFIX to deliver more information, slightly different way. And if you're familiar with this family of protocols, Juniper calls this protocol inline monitoring services. Cisco, again, lengthy, very lengthy, and we cannot use it as standard, as protocol name because there are more implementations than only from Juniper. And Cisco calls it just amazing way. Cisco calls it IPFIX 315. So if you love abbreviations, it's your choice. And so if you work for a vendor and if you have any idea about better naming for this protocol, please share it. I would love to have better name for this protocol family. How it works? As I explained it, as transport, it uses IPFIX or Netflow 9. And both protocols, they can carry any kind of information we have. And what happens and how it's different. So instead of parsing packet on router level, extracting source port, destination port, VLAN ID, VRF ID, how it works, it just encodes first 80 bytes of packet, wraps into UDP packet, and sends to collector. Sounds similar to sFlow, and it is similar to sFlow. That's exactly how it works. But there's a great deal of difference between in comparison with sFlow. First of all, it's implemented in hardware, because only two implementation we are aware and we have experience in operating at Juniper Max and Cisco SR9K and Cisco NCS. It implemented in hardware, so it addresses issues we had with protocol, with sFlow protocol. And in compare with sFlow, we have unlimited ways to express and provide more more service information, such as in this case, it's packet direction, it's ingress, it's input interface, output interface. And this is not limited because this one, I suppose, this one I collected for Juniper. For Cisco, it's a little bit more. We may have a source ASN number, destination ASN number. And by having all this information in place, we can detect DDoS efficiently. And we can access to every single field we have in packet. And also in the same time, we have access to service information about packet. And one significant difference of this protocol, it's implemented in hardware. And in compare with standard IPFIX or Netflow, this protocol doesn't involve any kind of aggregation. An aggregation process, it means to collect more data over some period of time, maybe 30 seconds, instead of sending information about every single packet. We wait and update information, send information to collect only about new flows or changes for same flow, for previous existing flows. When flow finished or when new flow started or but in this case, this protocol works on packet basis. Again, it eliminates need to have quite sophisticated kind of machinery inside of your routers, which involves lots of memory and lots of computational resources, which is flow aggregation engine. Instead, a router just picks up one packet from, for example, 1,000 of packets, wraps it in the IPFIX packet, and sends it to a collector machine. But it does it in hardware, without any issues. If your control plane overloaded and, or vendor messed it up somehow with control plane, it doesn't affect it. And for us, it provides tremendous benefit because in case of DDoS, we can see hundreds of gigabits of malicious traffic. But at the same time, we can see that every single information, every single piece of information about what was inside of this traffic will be delivered by routers. So I believe this protocol is a final step of what you are looking for. But of course, as this protocol was sampling, it uses exactly the same approach for sampling rate encoding, which was used by Netflow 9 and IPFIX. It's still complicated. But again, it's more like next generation. If your collector software already has support for Netflow 9, Netflow IPFIX, and sFlow, it shouldn't be that complicated for vendor to add support for this protocol. You may call it IPFIX 315, you may call it Inline monitoring services, because again, we have no name. But if you are looking for deployment of new net traffic telemetry protocols right now, and you run modern equipment, this is a protocol you have to look at. Because basically, if you start, for example, with Netflow 9, you will face issues with time. It may be scalability issues, it may be lack of information. If you start with sFlow, it may work for a few months. Then you will face issues. And by making choice in favor of this protocol, you will be in great position because you will provide very scalable way, because scales very well, provides lots of information, and it provides opportunity for growth. For example, if, for example, in my next decade, you will switch from Netflow IPv6 to something different, or we will introduce new kind of tunneling traffic, fine. It can be supported by this protocol because, again, it's not limited. It can have lots of additional information, maybe service information about traffic, and it can provide lots of, I would say, runway for this protocol, at least to be sustainable and usable at least 1 decade. It has lots of benefits, as I explained it. So, thank you for listening, and I would love to answer your questions. And in any case, I shared my contacts, and if you have any questions, and if you're puzzled by some issues in what you observe from your router, or you have any issues with DDoS detection, I will be happy to answer. And if you want to try our product, you can just Google FastNetMon, and you will find out our GitHub page. You may find how every single protocol I just explained how it implemented. You can read source code. You can find funny comments or developers had. And thank you for listening.
We have one question from the online community. Matt Peacock, SNMP-enabled engineer. Thank you for this talk. If the final IPFIX as transport for sampling protocol has no official name, how can we identify if a collector package supports it or not?
It's a great question. Again, in case we are aware only about 2 vendors who actually support it, and they have their own name. In case of Cisco 9K or Cisco NCS, you just need to Google your documentation for IPFIX 315, and you will find detailed guide how you can switch your standard IPFIX configuration into this mode. And in case of Juniper, it's called Inline monitoring services. And if you represent a vendor without support for this protocol, please come up with a better name and please implement it, because this protocol is just great.